Now let's apply this knowledge to a more complicated, or a different type of situation. It is a more complicated situation. Let's say we had an initial velocity of 40 meters per second at an angle of 30 degrees with respect to the positive x-axis. So the object is going to go up like this and then come back down, okay, following a parabolic arc. And let's say we have our same 20 meter, and I put a 20 there and I didn't put a meter on it. Let's put a meter on there. We have a 20 meter altitude here, a 20 meter drop. The potential energy change, as we saw before, is negative 196 meters squared per second squared times the mass, which we'll call big M again. The kinetic energy of the object, and this time I'm using KE0 for the initial kinetic energy, at 40 meters per second, our 1/2 mv squared is going to be 800 meters squared per second squared times big M. So this is our original kinetic energy. Now, what can we determine? If our original kinetic energy is this, and our change in potential energy is this, well, we're losing about 200 joules of potential energy, right? 196 joule loss. What's that going to do to our kinetic energy? If the only force being exerted here is gravity, that's going to increase our kinetic energy by 196 meters squared per second squared times M. So that the kinetic energy we end up with, which is of course 1/2 big M times the final velocity squared, is going to have to be the 800 meters squared per second squared times M, plus the 196 meters squared per second squared times M that comes from potential energy loss. We can do this formally with the equation, and we can see that if our change in kinetic plus change in potential is 0, our change in kinetic is final kinetic, which we said was 1/2 mvf squared, minus initial kinetic, which is 800 meters squared per second squared times M. And to that we're going to add the potential energy change, which is negative 196 meters squared per second squared times M. And that's going to have to all equal 0. We can easily solve this equation for VF. We first note that M appears in every term, so we can divide both sides by M. It'll disappear, and we end up with 1/2 VF squared minus 996 meters squared per second squared equals 0. We add the 996 meters squared per second squared to both sides, multiply by 2 and take the square root. Very straightforward calculation. We end up with a final velocity of 44 meters per second. That gives us the magnitude of the final velocity. How are we going to find the angle of that final velocity? Well, let's just look at what we've got. And let's zoom in on it. Our final velocity is at some angle, and that's going to be represented by VF, and we're going to note that that's 44 meters per second. We know our final x velocity here is still going to be whatever it was at the beginning. Now, looking back at what our initial velocity was, it was 40 meters per second at 30 degrees. We can find the x component by multiplying 40 meters per second by the cosine of 30 degrees. And when we do, I believe that the result rounds off to 35 meters per second. Now we have the situation. We have the x velocity. We don't know the y velocity, but we do know the magnitude of the vector. We can use the Pythagorean theorem. The square of this plus the square of this equals this, so that this is the square root of this one squared minus this one squared. And we get about 28 meters per second. Then we can take the, and of course that's negative 28 meters per second. I'm making a lot of mistakes here. Okay, that should be negative 28 meters per second. So we have the inverse tangent of negative 28, which is going to give us negative 34 degrees. Negative 28 over 35. The y over the x gives us 34 degrees. Question mark next to that. Verify that calculation. Actually, I think it probably comes out closer to 37 now that I think about it.